the recording is on. So today we have the pleasure to host Joe from Google DeepMind, who will tell us about their recent work, SIMA. So Joe Marino is a senior research scientist at Google DeepMind. His research focuses on developing principles underlying agency in AI systems, in part driving on inspiration from biological intelligence. Prior to joining Google DeepMind in 2021, Joe completed his PhD at the California Institute of Technology, Caltech, investigating connections between predictive coding in neuroscience and machine learning. Joe, we're super excited to have you there today, and it's all yours. The scene is all yours. Thank you.
All right. Thanks, Emil. So this is basically going to be mostly a repeat of a talk that I gave recently at the kind of department seminar at University of Edinburgh. I'm going to go through it a little bit quicker than I did then, because I'm assuming a few people have seen it, because I want to leave a little bit of time at the end for discussion. But feel free to stop me at any point during the presentation if anything is unclear or you want some clarification around that. So this presentation is centered around a recent paper that we put out called Scaling Instructable Agents Across Many Simulated Worlds. The kind of moniker that we've given this project is SIMA, which is kind of a bit of a backronym for Scalable Instructable Multi-World Agents. So just to kind of preface where things are at in the field, AI in the early 2020s so far has really been a story of generative AI. So we've had models like, apps like ChatGPT, Gemini, Anthropic's Claude, and these models can give very impressive outputs where you ask them natural language questions about things like videos, and they can give you very detailed answers about what's going on inside these videos. And these are definitely useful programming assistants, useful for idea brainstorming, kind of general purpose question answering tasks. And then likewise, we've also had a set of models around image models, video models, audio models, where you can do these impressive kind of combinations of different concepts with different styles. And this will certainly be useful for storyboarding, personalized images, music, etc. And you may even see something like a feature-length film in the near future. So this has been all very impressive stuff, but it's really a largely disembodied version of AI. And I think what a lot of people got interested in this field for is this notion of this interactive agency that AI could have. So what do I mean by embodiment exactly? Kind of formalize it as the degree to which a system can affect or control its sensors. And the kind of benefit of having this embodiment is that if you had embodiment and a large sensor space, you had a lot of sensors you could control, then if you could control those sensors, you'd be able to reach many states of the environment and solve many tasks. So it can do many useful things for us. So these systems are definitely doing useful things in the digital realm, but they're largely unable to control the physical realm that we inhabit. So I come at this from a bit of a biological or neuroscience perspective, where when you look through the literature of why it is that we even have brains in the first place, like what is the point of having a brain? You might initially think, well, it's something about intelligence, but that's kind of a fuzzy subject. And the more you dig into it, and the more you kind of look at the evolutionary history of kind of from a design perspective, why even have a brain, the theme that comes up over and over again is that the purpose of the brain is to coordinate the body's movement. That's not to say that it's all the brain does, but really at its foundation, that's the evolutionary purpose of having a brain, is coordinating your body. And so there's a recent book from Max Bennett called A Brief History of Intelligence. I think this really lays out this kind of perspective well. I'd highly encourage you to read it if you're interested in kind of this layman's perspective of why even have a brain. But it really starts with this foundation of steering. So learning from just direct interaction with the world, being able to steer your body. It then scales up to reinforcement learning, where you can now extend this over time. Once you get to mammals that have a cortex, you can learn from your internally simulated experience. When you start to expand the prefrontal cortex, then you can learn from observing others' experiences, this process of mentalizing. And then in humans, we have this ability to use language where we can learn from others simulated experience. But really, all of this is built on this foundation of steering. So at its heart, it's all control, all steering at this base level. So people have been trying to tackle embodiment with the modern AI systems in robotics, but consumer robotics really has not taken off yet. And it remains unclear whether it will in the near future, but it's really been difficult to scale these experiments because of the upfront and marginal costs. It's been difficult to gather very diverse data. So if you look at all these photos here, they're pretty sterile lab environments where they're collecting data. You have pretty limited experimental control because you now need to manually reset the environments, which just makes research very challenging to perform. And you have all these safety considerations. So it's huge liability if you were to release one of these systems in the real world. If you made a mistake, that would be just potentially catastrophic. So these current robotic systems live in a pretty impoverished sensory environment. And so the research in robotics has been relatively slow. I think it should pick up hopefully pretty soon, but so far it's been relatively slow due to all these issues. So a lot of people, and DeepMind helped pioneer this kind of perspective, have turned to games and simulated environments for doing research. So if you go back to like kind of the pre-deep learning days, like early deep learning days, there was obviously the work on Atari that kind of launched all of deep reinforcement learning. And you had, following up from that, a lot of work in environments like Minecraft, Doom, these kind of Sega environments that we're now expanding to all these different types of embodied environments in these simulated domains. And then toward the end of the 2010s, so 2018, 2019 kind of time frame, you had OpenAI 5, and then you also had AlphaStar. So you had these really massive scaling up projects of just like let's try to tackle and beat humans at these massive strategy games. And what we saw along this progression was increasingly complex observations, actions, and dynamics in the environments. But we also saw largely single domain types of approaches, especially as we got toward Dota 2 and StarCraft. We had kind of bespoke action spaces for the most part, and you had a relatively limited number of tasks and limited ability to specify tasks. So you're really just trying to beat the game in all of these different environments for the most part. And one thing that I think maybe got overlooked from this mid-2010s kind of era was this notion of a universal interface or universal agent, where because you have this keyboard and mouse and screen type of interface, that allows you to interface with any kind of environment that a human could potentially interface with in a video game. And because you have this universal interface, now you can tackle really truly multi-domain setups. So you can apply your agent to any, in this case, any Sega environment and potentially learn from all the diversity of that. So that's not to say that these mid-2010s era approaches were without their limitations. So if you look at the universe, it's really high in vision and action diversity. So there's a lot of different visuals that you have there, but it's still quite limited in terms of the trajectory diversity. So you're still always just trying to win the game. You're never trying to do some random thing. You're always trying to win the game. You're always getting this reward for winning the game, which you can conceptualize as this kind of like, it's this very detailed mountain landscape, but it's still only kind of one path that you're taking through that landscape. And then likewise, you had all the Minecraft work, which obviously has a fair amount of visual diversity as well, but it's really just this one kind of voxel environment that you're dealing with. And so you have a lot of different things you can do. You can build all sorts of bases and whatever it is, but you have still somewhat limited visual and action diversity because it's really just all contained within Minecraft here. So in this new kind of era, as we push forward in simulated agent research, we kind of want to target this space in between where we have both high diversity of trajectories. So you're doing a lot of different tasks, but you also have high diversity of vision and action dynamics. So you're tackling all sorts of different environments, not just Minecraft in particular. And that's where SIMA comes in. So SIMA stands for Scalable, Instructable, Multi-World Agent. And the main kind of tagline you can think of it for it is a single agent with a universal interface that can be instructed via language to perform any task in any 3D visual environment. So let's unpack that quickly. So a single agent, so we have just the SIMA agent. It has this keyboard and mouse and vision interface, this universal interface, same interface that humans use to interact with the environment with these kind of games. You have the agent being instructed via natural language to perform various tasks. And now in a given environment, like the No Man's Sky video game, we want the agent to be able to perform any task. So I might tell it, go to the spaceship. I might tell it, shoot the asteroids, land the spaceship, mine dihydrogen, use a jetpack, open up the deployable technology menu. Any of these tasks, I want the agent to be able to do these things. But not just in that environment, but any 3D visual environment. So we have all these different types of video games that we want the agent to be able to perform potentially any task in those games. So it's really about scaling up, again, both the trajectory diversity, all the different tasks, as well as the vision and action diversity in all these 3D visual environments. So just to overview the different components that make up the SIMA project that we've been working on, we have a large set of environments. We've partnered with a lot of game studios to use their games as research environments. And then we also, as environments for training our agents. And then we have separately these research environments, which many of which have been developed in-house, but we also have some other academic environments like Proctor. So this is kind of building on some of the legacy work that DeepMind did in these kind of embodied environments and simulation. Once we onboard an environment, we now go and collect a bunch of data. Initially, we're collecting human data, and we're building up this data set consisting of the vision, the actions taken, and a text description of what the task is. We're then feeding that into an agent that has some pre-trained models inside of it, and training purely with behavioral cloning for the moment. And that's giving us this SIMA agent. And then now we feed that into our evaluation pipeline, some of which consists of human evaluations of did the agent successfully accomplish this task or not. And then that results in these trajectories of behavior of agents attempting to perform tasks. So here we instruct the agent, pick up leaves. It's right in front of the leaves, and it knows, okay, I need to go over to this bush. I need to press E in order to collect the leaves. And that consists of performing that task. So to go through these in a little bit more detail, for the environments, you'll notice that we really wanted to focus on 3D visual environments with either a first person or potentially third person kind of perspective. So it's just a single agent performing tasks, much like you or I would if we were just navigating our visual environment. We want these to be relatively complex and open world kind of sandbox games, instead of just, if you think of those old Sega games, you're really just trying to perform that one task, just get to the end of the level or whatever it is. And ideally here, we want these games to be interesting to humans, because humans are going to be the ones playing and judging performance in these games. We wanted to stay away from a focus on violence. So a lot of games are focused on killing, and it's not really the most interesting set of tasks. It's also not an area we really want to focus on. And then ideally, we want a lot of diversity across the different environments. So what we ended up with to start was Goat Simulator 3, which is a environment where you're a goat going around causing havoc. Hydroneer, where you're constructing these kind of contraptions out of different pipes and things like that. No Man's Sky, where you're going around mining minerals on different planets. Satisfactory, where you're building factories, harvesting different resources. Teardown, where you're carrying out heists and destroying parts of the environment. Valheim, where you're a Viking going around and again collecting resources, building your hut, getting armor, and then wobbly life, where you have to go around and complete a variety of different jobs, buy a house, kind of this kind of fake Plato kind of world. And then in terms of research environments, we developed this environment called Construction Lab, which is focused on really building things in this kind of simulated factory environment. Playhouse, where you're inside a house, you do things like cooking, picking up objects. Proctor is this academic environment, and then World Lab is you're basically picking up blocks, opening up doors, activating sensors, things like that. In terms of data, we again focused on collecting human data initially. We have two main ways that we've gone about collecting data, one of which is this one-player setup where a human's playing the game, annotating what they're doing, and a two-player setup, which we call setter-solver, where it's one human telling another human, here, do this task, and then the other human carries out that task in the game. And so this gives us our data set, and when we cluster the types of tasks that are being performed within this human data, we see a wide variety of different tasks. So it's really what we want to see is this diversity of tasks, diversity of trajectories, where we have a lot of tasks focused on navigation, objects and tools, construction, animals and plants, and then you have a whole long tail of things going from combat to food to crafting and things like that. In terms of the agent is not highly complex. It's really kind of a vanilla architecture, but I'll walk you through a few of the things that we found helpful. So the overall setup for this agent is one in which it's receiving the visual input from the environment, it's taking keyboard and mouse actions that are being fed to the environment, and that environment is running just in real time. So the agent has to compute and cannot is not in lockstep with the environment. And user is supplying language instructions to the agent throughout in just natural language. So just to zoom in on the agent portion of this, we have this visual input, which is being fed into two different visual encoders. We have this Spark contrastive image language encoder, which basically is like a clip style model, but with a bit better spatial awareness. We also have a separate visual encoder, which is Finaki, this generative video model. And then in addition, we have the text encoder, which is just a transformer that's feeding in these text tokens. There's some cross attention going on, and then memory transformer XL. And then that's being fed to a keyboard and mouse policy, which is just a set of MLPs. And the one thing I want to highlight at the output is this notion of classifier-free guidance. So this is an idea that was really developed more in the generative image modeling literature, but can equally be applied to behavioral cloning type approaches, where you have this this text conditioning that's coming in of perform this task, and so you can say, okay, here's what my logits would be for my policy with this text conditioning. So that's this conditional, this mu conditional, and then here's what my text conditioning would be without this conditioning, this mu unconditional. And I take the difference between these, and I basically push my conditional logits even further in that direction with this lambda controlling the amount to which I do that. So it's really just saying, be even more conditional than you otherwise would be. So it's kind of a way of doing action or policy inference in this kind of cheap way. So that seems to be incredibly beneficial. I'll show one ablation toward the end that shows the benefits of doing that. And then finally, on the evaluation side, so in order to actually assess, did the agent perform this task or not, we need some starting state, we need an instruction. So in this case, put the frying pan on the stove. We need some way of assessing the success of the task. That's either the ground truth from our research environments. This could be OCR, which is just like detecting text that's on the screen. Could be human evaluation. And then we bundle up a set of tasks for a given environment, and that becomes our challenge. So to walk through that, the ground truth assessment is just you have some parameterization of like, is the Y position of the marker greater than 0? If so, then success is true. This gives you a very accurate automatic evaluation, but it's really just restricted to these research environments. Whereas for OCR, it's a little bit more widely applicable because you can now apply this to our commercial video game environments. So here we're detecting as raspberries appear in this box here, but it's really just restricted to state changes that involve some text appearing on screen. But the most general way of doing this evaluation is to just ask a human, did the agent go upstairs? It's very flexible and widely applicable, but also very costly if you have to send a video to a human in order to assess for every single task you try to perform. So that's the setup that we're dealing with for the moment. Again, it's all collect human data, perform behavioral cloning, and then we have this set of evaluations to assess, is the agent actually performing these tasks well? So now I want to get into the results. So the first thing you can look at is just these kind of domain general behaviors. So any 3D environment should allow you to do very basic kind of spatial navigation and object interaction types of tasks. So we can look at something like go forward, where you tell the agent to go forward, and in all of these games, go forward is generally the W key, and so the agent has learned, okay, go forward means just press W, and so it goes forward in all these different games, despite the different visuals. And you can do the same thing for turning left, turning right, turning around. Interacting with an object is usually something like E or F or clicking. And then menus are typically either something like escape or tab, or maybe M for the map. So it's because you have this shared interface and there's a lot of commonalities across these different games, there's some kind of overall just domain general behavior that you inherit by training on all these different games. But what's a little more interesting is when you get into these domain specific behaviors. So in No Man's Sky, you can ask the agent to go to the spaceship and it'll look around for the spaceship, find it, then navigate toward it. You can tell it similar to feed a creature, it'll find the creature. Or use a jetpack, you shoot an asteroid. For Valheim, similar things, you can tell it to pick up mushrooms, chop down a tree, craft a club using the menu, or fight a grayling. In Goat Simulator, similar sets of types of tasks, but now very different objects you're navigating to. Some domain-specific things like this particular building is called the Goat Castle, and you need to know that if you want to be able to navigate toward it. And then similar things across different environments. So what I'm showing here is primarily navigating toward objects. There's a little bit of menu use, things in that realm, and you can still handle the specifics of each of these environments here. Just to kind of back that up a little more. So even though, again, you have like specific words like spaceship or tractor or a blue car versus a purple car or a boat versus a truck, there's a lot of commonalities associated with these tasks where you need to look around, identify where this vehicle is, navigate toward it, and you usually press something like E to actually get into the vehicle. So there's, again, a lot of commonality across these different tasks and things that could transfer, even though the specifics of the language, the specifics of the visuals, and maybe some of the specifics of the actions might be slightly different. So that's kind of the qualitative level of where things are at. And I think it's very exciting to see, but what's more important is maybe to look at some of these quantitative metrics just to assess where we currently are. So this is our absolute performance on our evals as when we published or put the paper out. And so this is showing the success rate across all of our different tasks for a given environment. So again, we have the Playhouse, World Lab, Satisfactory, Construction Lab, No Man's Sky, Goat Simulator, and Valheim. At the time, we didn't have evals for our other domains, but we see that generally the agents can perform a fair portion of these tasks, but are far from perfect across these different challenges. So there's still quite a ways to go to get to really just mastery of these environments. So there's still some room for improvement here. We've also broken down the performance by different skill categories. So we've looked at our tasks and assessed, does this involve, for instance, stopping, moving, looking around, combat, or using tools. We're still kind of parsing through some of these task or skill level performance metrics, but the main thing, which I think kind of makes sense, is that tasks that require more precise control are generally a little bit harder to perform. So if you need to build something, that's generally more difficult than dismantling something. So it's easier to destroy than it is to create. And similar things for like combat. It requires identifying this enemy and locking onto them and combating them. So that was, again, in terms of absolute performance on these different ways of parsing the tasks. But what's, I think, a little bit more interesting is to look at these ablations. So we can compare the full SIMA agent, where we train on all the domains and we eval on all the domains. So this is like No Man's Sky, Goat Simulator, so on and so forth. And so this agent has these pre-trained models, which I'm showing as these gears, and it's also receiving the instruction. So we can compare that with an environment-specific agent. So it's the same agent architecture, but we just train on a single domain and we evaluate on a single domain on the same domain it was trained on. Then we can look at something like a zero-shot type of agent, where you train on all but one domain and then see how do you perform on the one you were held out on. We also can look at an agent without the pre-trained models inside of it, that Spark and Funaki vision encoders. One helpful way to assess how language conditional our evaluations are is just to remove the instruction from the agent. So it hasn't ever seen an instruction before. It's just kind of said, oh, okay, this is a reasonable action to do in this kind of state. And then finally, for a subset of the tasks for No Man's Sky, we looked at humans performing those tasks. So it's a human who has played No Man's Sky before and then is evaluated on No Man's Sky in the same setting that our agent is evaluated on. So this is a aggregate over all of our different environments here. And so what I'm showing is the relative performance relative to this environment specialized agent. So this is per environment. This is the specialized agent performance. So it's normalized to that performance level. And then it's expressed as a percentage, a relative percentage. So the SIMA agent we see vastly outperforms this environment specialized agent. The zero-shot agent, so this is an agent that's never seen that particular environment before, performs almost as well as that environment specialized agent. Without pre-training, it performs roughly on par. And then without language, it performs much worse. So just to unpack what these imply about kind of the training dynamics. So we have positive transfer across our different environments. We have a fair amount of generalization, where we can actually perform almost as well as the environment specialized agent without ever having seen that environment before. This goes back to like those kind of general navigation tasks that we talked about. Pre-training is definitely helpful for our agent. So having those pre-trained vision models is helpful. And finally, our evaluations require language, which is just a helpful sanity check to make sure that it's not kind of obvious from from where you start out in the task exactly what you should do. You do need language in order to perform that particular task. So that
Joe,
was the.
sorry to interrupt you.
Mm-hmm.
Just had a quick question. Does the environment specialization see the same number of interactions as SIMA in total?
So it's seeing just the data for that particular domain. So it's a fair point that the SIMA agent is seeing many more state transitions overall, whereas the environment specialized agent is seeing just for that particular domain, but they're seeing an equal number in terms of, they're seeing the same amount of No Man's Sky data and then evaluated on No Man's Sky.
So that means that they're seeing the same amount of No Man's Sky data than the SIMA agent saw on No Man's Sky, but it doesn't get n times the amount of No Man's Sky data.
No, yeah. We also keep the number of frames consistent across the different evaluations. So this agent has been trained for a similar number of steps. But we also have tried to make sure we're not like the environment specialized agent hasn't totally overfit to that environment, if that makes sense. So we're trying to make sure everything is totally fair comparison, keeping the amount of data per domain consistent.
So it's the same number of steps per game, or same amount of overall steps?
Same number of total training steps. So it may have seen, so the environment specialized agent may have seen a given state multiple times, potentially.
Oh, I see. Okay, so it's more epochs, but the amount of data is the same, but it will get more epochs of No Man's Sky because it runs the total amount of steps. Okay, I get you. Thanks.
Yeah. So that was the aggregate. So if we break this down into a per environment breakdown of those same relations and comparisons, we see across all the environments we have transfer. So the SIMA agent is outperforming the environment specialized agent in all cases. The amount of generalization does vary a bit, and this might depend on how much similarity there is across different environments. So there might just be more unique things about the construction lab as compared with, Goat Simulator 3 in terms of our evals. The pre-trained models, so looking at the difference between these two bars, the pre-trained models are always helpful, but to varying degrees across the different environments. And then again, our evaluations all depend on language, but for instance, in our satisfactory evaluations, they depend on language to a lesser degree than in the Playhouse, for instance, where you maybe have to cook a particular object or cook a particular type of food or something like that. So now moving over to looking at classifier-free guidance. So we evaluated an ablation without classifier-free guidance on the research environments that we have. So we have Playroom, Construction Lab, and World Lab. And here we looked at the SIMA agent, which has this classifier-free guidance, so being even more conditional than you usually would. And then we're comparing that with an agent that has just a normal text conditioning policy logits. And so there's this fair amount of difference between these two agents in terms of performance. So the CFG is quite beneficial, but it's still, even without using classifier-free guidance, the agent is still much better than if it didn't have language at all. So it's definitely still conditional. It's just not as conditional as if you had classifier-free guidance. So this is really a bit of a cheat code, and it seems to work very well. This is one of the main takeaways that we had from this line of work. And then I think one of the final ablations I'll show is comparing with human performance. So our agents, while they can do these small types of interesting tasks, they're still not performing on par with humans. So this is for a subset of tasks on No Man's Sky. We see that even humans are struggling to reach 100% success. We have pretty stringent success criteria. So if you do even one kind of action that's not like getting you toward accomplishing that task. So if you open the menu accidentally or for whatever reason, instead of mining the thing that you were instructed to mine, then that will be counted as a failure. So this is humans evaluating other humans. And we see that even humans struggle to reach 100% success, but our agent's still far from matching human performance. So there's still quite a bit of room to go to reach that point. And then again, the other agents are performing a little bit worse, but yeah, still quite a bit of room to make up if we want to reach human level performance. So in the final kind of closing remarks here before I get to discussion, I think a lot of people are after this kind of North Star of a general purpose humanoid robot. And there's a lot of challenges to overcome if we want to get to that point. And so I think one avenue to explore is this use of simulated environments, and especially commercial video games is one way of developing some of the basic research aspects if we want to get to actually having these systems in the real world with us. And a lot of the previous works have lacked diversity in terms of the trajectories, where you're just trying to beat the game. You're not trying to do every possible thing you could do in the environment, or you're really just restricted to this one environment like Minecraft, where you have some lack of diversity in the observations and affordances. And we really see Sima as kind of the next generation in this line of research, where when you go from Atari to, excuse me, Minecraft to StarCraft 2 and Dota 2, when you finally get to Sima, I think it's just massively expanding the diversity of both the observations as well as the diversity of the tasks and trajectories. And we think this is a very important kind of direction to push for actually being able to develop basic research ideas around embodiment in these simulated environments. So we believe strongly that this is a useful direction to push if we want to get these insights into creating AGI. And I like to think of Sima right now as basically at the pre-training phase of general purpose behavior, where you can instruct the agent, go chop down a tree, and it will very reasonably look around, find a tree that is small enough that it can be chopped down, navigate toward that tree, start chopping down the tree, collect the wood, all extremely reasonable behaviors to do. So it's kind of this glimpse of this general purpose behavior. And I think it's somewhat analogous to this previous era in language models, where if you look back at like the GPT 2.3 kind of era of models, you had, excuse me, you had like this blog post from back in 2019 where they were showing like, here's an output from GPT-2, and it can reasonably continue this news headline. And what I think this is showing is kind of like not a really properly general purpose model yet, but kind of this glimpse of this impressive capabilities. So much like language models, I think it really could just be a handful of innovations that take us from this pre-training phase to a much more general purpose type of agent that is capable of performing any task in any simulated 3D environment. And the final quote I'll leave you with is from Jim Fan from NVIDIA, where he says, if an agent is able to master 10,000 diverse simulated realities, it may well generalize to our physical world, which is simply the 10,001st reality. So this really paints this picture of, if we can do any task in any simulated environment, we'll maybe have figured out general types of strategies for dealing with these 3D environments, and that ideally would translate at least into some type of insight for how we might tackle this in the real world with robotics. So the Sima team is a very broad set of people that have all worked on this. I'd ask you to go check out the paper. We have a blog post as well if you're interested in learning more. And with that, I will leave it to discussion. Thank you.
Thanks, Joe. Thanks a lot for the talk. And I got booted out in the meeting in the last second, but I just got back on just in time to give you the outro. So yeah, so we're going to open the floor for questions now. Maybe I will open with one. So I was wondering, I think it's back on slide 27, based when you are like considering different ablations of Sima.
Yeah.
And
yes.
Or maybe it's 28. Sorry. Yes, this one. No, 27. It's 27.
Yeah. Okay.
Or the one with the zero shot. 26.
Yeah, I mean this. So this is the aggregate
one.
Okay.
Yes. So essentially, So I see a slight different like interpretation of the result on like comparing the first two baselines between Sima and zero shot, because so the generation gap is usually measured would be like the difference between Sima and zero shot, right? And so that tells me that like SIMA overfits quite a bit to the training tasks, but at the same time, it's unfair to expect the exact same performance on a game that you've never seen. As a human, an AGI would not necessarily, or an AGI would not necessarily be able to perform as well, because there's a lot of like context specific thing to each video game, right?
Yes.
But I'm just thinking like it's maybe almost of a philosophical question, but how do we disentangle overfitting from this sort of domain specific knowledge that you need to have, and also like what do you take of like the very big difference in SIMA and the zero shot baseline? Is this like something that is mostly due to the context specific of the game, or like more of an overfitting behavior?
Yeah, it's a really good point. I think it's hard to say whether or not this is really overfitting versus just context specificity. Like that, I think that breakdown isn't really clear from just these two bars here. That's certainly something we could look at is like the difference between these two bars. Is this entirely due to just you've never heard this particular word before, and so you wouldn't know, okay, that's what that object is, or like that's what this menu refers to. So I think, yeah, it's unclear whether the agent is actually overfitting. I'm not sure I would go as far as to say it's overfitting to its environment, but I think we definitely want it to be able to take a small amount of data that just refers to the objects, use a small amount of that data to then massively improve from the zero shot to the full multi-domain setting.
Yeah, no, it's very hard to disentangle the two, right? And well,
yes, good point.
what I take is like the positive transfer though makes a lot of sense, that if you have like more data, more games, that you're able to train faster than if you only have access to a single game. But yeah, I think we need a progress in this evaluation metrics, other ways we can if there is any way even to disentangle the two, because it's very hard to then know if you should regularize more, or you should accept that your agent should have some degree of specialization.
Yeah, I think having a better breakdown would be helpful for sure.
Thanks. And do we have any other questions from the audience?
Hey, Joe, thank you very much for doing the presentation. Really appreciate it. It's nice work. I think I'm trying to understand a bit better exactly what data you actually need, and what the sort of how difficult it might be to get that data, or what the main properties are of the data in order to make this approach work. I looked at the paper again, but I was wondering if you could sort of run us through this again. I think you had a slide about that.
Yeah,
I'm not sure I'm getting the full picture there.
So the data itself is a set of everything that's fed to the agent. So it's the vision, the keyboard and mouse actions, and the text for a particular task. And this is so that's what's fed in. Again, the vision, the keyboard mouse actions, and then the language instruction. And so that's collected from either this one-player setup or the two-player setup here, where you're either you're a person playing the game for yourself, you're going around solving tasks and then annotating, here's what I'm doing at this time step. Or you're in this kind of setup that's a little more similar to what the agent would experience, where it's a person giving text to another person saying, hey, do this task. And then that trajectory is then annotated with, oh, this is the goal you were given to solve.
Okay. Just let's stick with the first version, which is when the thing on the left. So I think I'm trying to understand better how this works. So should I imagine basically I'm running through this game? So the vision input and the controls, that's straightforward, right? I understand that, but I think I'm trying to understand the text part a bit better. Does that mean basically there will be different points in time where I initiate executing different sub goals, like go to A to B, from A to B, open door, pick up this or something? And each of these are basically temporally extended actions, right? That require a number of time steps. And does that mean that basically each one of these subtasks produces a sequence of inputs and outputs in terms of the vision and the controls, and you basically copy and paste the same text annotation for each of these subsegments? Should I imagine it like that?
Yeah, exactly. Where you have this rolling kind of over this section of the trajectory. This is the corresponding text task that's being performed. And we've kind of chosen some. We've chosen some kind of roughly arbitrary, like 10-ish second horizon for defining these tasks, but you could obviously describe them at different levels of granularity.
So is it the case that I, as the annotator, I have to say, okay, now there's a new starting point, and this is the text level for the next subtask, or is it fixed intervals, and then I get prompted for each of the fixed intervals?
No, I decide here's when a task starts, here's when it ends, and this is what the text corresponds to over that span.
Okay. So I guess you build an interface that makes it easy to do that for the human player, basically going through this game.
Yeah, exactly.
Okay, and I guess you'll have to tell the human user that they need to understand this idea of subtasks so they can realize when one thing starts and the sort of and ends, right?
Yeah, there's a lot of instruction that's given to our human data collectors and annotators as to how to label these things.
Okay, that's a sort of an interesting meta question, right? Do they actually, like, at what level of granularity should they be able to identify and segment these subtasks in order for the method to work? Some people could have a pretty high level understanding of this, and others might go down on a fairly low level in the decomposition, right? In some sense.
Yeah, it's a very fair question, and I think at least to get started, we kind of just chose a particular time horizon, which is like this roughly 10-second to maybe 30-second task horizon. But that's a choice, and I think definitely not. We shouldn't restrict ourselves to that particular horizon. And so a more general approach would involve figuring out different horizons of different tasks automatically.
Yeah. Okay. I think I understand a bit better now. The other comment I had was, so I think you made this interesting comment, at least when you presented in Edinburgh, at the end of the talk, how you're feeling there's this transition from GPT-2 to 3, right, that we need to make and so on. I actually had a different sort of transition in mind, which was relating to the data. The kind of analogy that I'm seeing now as the next step is between AlphaGo and AlphaZero, which is at the moment you need this huge human prior, which is all the annotations, right? And that's what AlphaGo did to bootstrap. But then we made that leap to AlphaZero, which doesn't require that anymore, which is nice, right? So that was like a nice step forward. And I'm kind of thinking it would be nice to make that transition with this work now, where we don't rely on that human prior anymore. Do you think that could be feasible?
Yes, and that's a very good description of where we need to head. I think there's one, well, maybe two complications with that analogy, though, is that we're like not even at AlphaGo yet. We're like at the initial phase of just the VC part of it. We haven't even done any self-play yet, which is impressive that it works this well even so far, but we have still even the self-play part to go. I think the one complexity is that, sure, you could put this agent in an environment and just let it go around, figure out, oh, here's all the things I can do. But ultimately, we do want to be able to interface with this agent and have it carry out tasks that we want. And so that interface part of it does require some amount of human interaction. So I think it's kind of unclear at what level we want to specify that. Whether the agent should pick all the text and language from the game itself, and then somehow we know how to interface with it, or whether we need to be in the training loop.
Yeah, super interesting. So I'm guessing you guys are already working on this now?
We are not necessarily doing anything AlphaGo specific, but I think definitely making the system more general and moving beyond human data alone is definitely an interesting direction to push.
Cool. Thanks again for doing the talk. Really interesting work.
Thank you.
I was wondering as well in the parallel direction of getting more data, more human data, but in a more economic way. Like, do you see that we're going to see like CAPTCHAs in the future where instead of identifying the stop sign, you have to label like a
you have to build a base or exactly.
Yeah, or you play for free. The game you would pay for normally, but you have to do a bunch of captchas to like unlock
exactly
the next level.
I wouldn't mind doing that, but
I don't think it's like that bad. Like, it's not. It doesn't raise any like ethical concerns with me actually. Could be a good way to make it economical actually.
I have another question.
Yeah, Caleb, you have a...
Cool. Yeah. Is my sound okay?
Yep.
Yeah.
Okay. Cool. Thanks for the talk, Joe. I really enjoyed the presentation, and I also enjoyed your talk in person. I guess my main question is related to the text annotations. Do you think that they're helping the agent actually solve the problem better, or do you think that I guess because you like the language is part of the evaluation, so it's hard to see, like, is the agent learning to solve the problem better because of the text, or is the agent, it's hard to evaluate the agent without the text input? I'm not sure if that's clear, but essentially I'm just wondering, like, is the language helping the agent solve the problem, and is there a way to measure that?
In terms, so it definitely, like, the evaluations do require language. So in that sense, yes, it is helping. I think maybe if I'm understanding, like, you're kind of asking, is text a useful way of encoding tasks? Is that maybe what you're trying to get at?
Yes, I guess you can say useful way of encoding tasks, or useful way. Yeah, I guess the texts are used to describe the goals that the agent needs to do. So the agents, I guess, need the text to know how to, or to know the goal. But is the text helping the agents? I guess it's a little bit tricky, because usually in reinforcement learning you don't have this text input, and the agents learn through interaction and they get the reward. And I'm just wondering,
what kind of task typically in those settings, or maybe you could do multitask, but
so they're usually solving and they don't have this text input. And I guess in this sense there isn't a notion of a reward, it's more the text is the goal. So I'm just wondering, in, like, let's say standard reinforcement learning context, and you included text data for your agent, with the text data, as opposed to encoding the goal, help the agent solve the task easier?
So that's a very fair question. I think the people with a more cognitive science kind of background would probably say yes, language is super useful because it has all these compositional properties that allow you to then, like, if you've learned how to, like, go to X, then, like, now if you swap that out for some other thing, you should kind of be able to say, okay, go to means navigate toward, like, so I think there's definitely a lot of compositional benefits that should allow you to transfer information across different tasks. I don't think we've definitively shown these types of benefits to language in our specific work. We need to still dig into the results a bit more to understand exactly where task knowledge is transferring. But I think in that sense, it should be helpful. I don't know, though, to what degree task is also a hindrance, like you're talking about, where there might be some aspects of a goal that are just very difficult to describe in language, and being forced to always operate through this bottleneck of language might just be a little too restrictive in some circumstances.
Okay, cool. Thanks.
There may be like a paper relevant to what you were asking about, Caleb, is by Amy Zhang. I think that's the paper. I'm not 100% sure because it's been a while, but it's essentially, they said that there's this benchmark where you have different tasks, and before people would give just a task ID as a conditioning for like the policy of the agent. So you would do like open the drawer or something like that, or close the turn off the sink, so like this simple task in a household, I believe. And then they just replaced the ID with the metadata describing the task, which is usually just for the practitioner to understand what the agent is supposed to do. So you can just read the code and understand, right? And they found that like, it actually improves quite a bit the performance, because there is some regularity in the language that you don't have with label IDs, which are just like completely orthogonal to each other. So yeah, maybe that paper is relevant in that.
Cool, thanks. We'll have a look.
Awesome.
I think we have a question from the audience. I don't see the name, but you can unmute yourself.
Okay.
Alain, it's you have your hand up. Did you have a question?
Does not allow me to speak.
Yeah, you are muted right now, so maybe like unmute yourself. Otherwise, maybe someone else can ask a question in the meantime. Maybe it's just
yeah. Otherwise, I'm happy to take any questions offline as well if people want to reach out to me.
Well, we did pass the hour, so do you have to be out very soon?
I should probably vacate this room. Yeah, but
okay.
Yeah.
Okay, well that's good. That's all good. Like it was very interesting, like discussion, and yeah, I mean your email is quite easy to find, so I think.
Yeah.
But yeah, thanks for coming today. It was really interesting.
Thanks for having me.
Yeah.
All right. Thank you, everyone.
All right. Bye.
Bye.